Welcome to our second set of mathematics practice questions for this course. In this video, we will dive into practice questions involving algebra and linear algebra. Ensure you have the FE Handbook open and reference its material throughout this lecture, as you must become familiar with it before exam time. As a supplement to this course, I have created full-length practice exams and other topic-specific practice questions that can be accessed through the link in the description. These practice exams are the best way to prepare yourself for taking the actual FE exam. Follow the timing requirements to mimic testing conditions and review the detailed solutions to learn from your mistakes. Moving on, let's get started with some mathematics practice questions. Practice question 1. Which of the following statements about power series are always true within their interval of convergence? Select all that apply. A. A power series may be integrated term by term, provided that the limits are within the interval of convergence. B. Two power series can always be multiplied together, regardless of their intervals of convergence. C. A power series may be differentiated term by term within its interval of convergence. D. Division of one power series by another is possible using long division, but only within the shared interval of convergence. First, we look at whether a power series can be integrated term by term. This is a fundamental property of power series. As long as we stay within the interval of convergence, we can integrate the series one term at a time, and the result will still converge correctly. So statement A is valid. Second, we evaluate the claim that two power series can always be multiplied together. This turns out to be false in general. Even though multiplication of power series is possible, it only works correctly when the intervals of convergence for both series overlap. If the intervals don't intersect, we can't guarantee the product will converge. So statement B is incorrect. Third, we consider whether we can differentiate a power series term by term. This is another classic result. Within the interval of convergence, differentiation of a power series is valid at every point, and the resulting series still converges. That makes statement C correct. Fourth, we check the rule about dividing one power series by another using long division. This technique only works within the shared region where both series are convergent. If we're outside that shared interval, the result of the division might not make sense. So statement D is also true, but again, only within the interval of convergence. Putting it all together, the correct statements are A, C, and D. Practice question 2. Solve for x in the following logarithmic expression. Remember to use your log identities for this question. To begin, we recall a logarithmic identity. The sum of two logs with the same base is equal to the log of the product of their arguments. In this case, the log base 2 of x plus the log base 2 of the quantity x minus 2 is equal to the log base 2 of x times the quantity x minus 2. Once we've combined the logs, we remove the logarithm entirely by converting to its exponential form. This allows us to isolate the expression inside the logarithm and set it equal to the exponential value on the right-hand side. This step gives us a quadratic equation in standard form. At this point, we apply the quadratic formula. Solving the quadratic gives us two values. We evaluate both roots, but remember, because we're dealing with logarithms, we must check that the values make the original expressions valid. Since a log is undefined for 0 or negative values, we discard any result that doesn't keep both expressions inside the logs positive. That leaves us with a single acceptable solution. We evaluate it approximately and find that it most closely matches option C. Practice question 3. What are the cube roots of the following complex number? Write each root in trigonometric form using angles in degrees. We're given a complex number in polar form. The magnitude is 8, and the angle is 120 degrees. We're asked to find the three cube roots of this number. To solve this, we'll use the general formula for finding the roots of a complex number. This equation can be found in the FE Handbook. First, we take the cube root of the magnitude. The cube root of 8 is 2. This tells us that each of the three roots will have magnitude 2. Now we compute the three roots using our formula. For the first root, we plug in n equals 0. For the second root, we plug in n equals 1. And for the third root, n equals 2. We leave the answers in trigonometric form because it's the most natural and exact representation for problems involving complex roots. Combining all these roots, we get the final answer as shown. This result matches option A. Practice question 4. Which of the following statements about eigenvalues and eigenvectors is always true for any square matrix? A. If all eigenvalues are 0, then the matrix is diagonalizable. B. Every square matrix has a full set of linearly independent eigenvectors. C. A matrix with distinct eigenvalues has a complete basis of eigenvectors. D. If a matrix is invertible, it has only real eigenvalues. Recall a core result from linear algebra. If a matrix has as many distinct eigenvalues as its size, meaning for an n by n matrix, it has n different eigenvalues, then it also has n linearly independent eigenvectors. This means that the matrix can be diagonalized, or in other words, written in a simplified form where its behavior is easy to understand. So this idea that distinct eigenvalues give us a complete basis of eigenvectors is a powerful and reliable property, and it sets up option C as a likely correct answer. Next, we evaluate the other choices by thinking about when they might fail. Option A says that if all eigenvalues are 0, then the matrix is diagonalizable. But this isn't guaranteed. A matrix can have only 0 eigenvalues and still fail to be diagonalizable if it doesn't have enough linearly independent eigenvectors. So that statement isn't always true. Option B claims that every square matrix has a full set of linearly independent eigenvectors. This also isn't always true. Some matrices, called defective matrices, lack enough eigenvectors to form a complete basis, even if they are square. So that option is also incorrect. Option D says that if a matrix is invertible, then all its eigenvalues must be real. But this isn't correct either. Invertibility only tells us that 0 is not an eigenvalue. It says nothing about whether the remaining eigenvalues are real or complex, so this one is also false. That leaves us with option C as the only statement that is always true. If a matrix has distinct eigenvalues, then it will always have a full set of linearly independent eigenvectors. Practice question 5. What is the magnitude of the resultant vector of the following three vectors? Each vector only contains x and y components. First, we add the three vectors component by component. That means we combine all the x values from the three vectors, and then we combine all the y values. The x values are 2, -3, and 4. When we add those together, we get 3. The y values are -1, 5, and 2. Adding those gives us 6. So the resultant vector is the ordered pair 3, 6. Next, we apply the magnitude formula for a two-dimensional vector. The magnitude is found by taking the square root of the sum of the squares of the two components. Finally, we simplify. The sum of 9 and 36 is 45, and the square root of 45 is the magnitude of our vector. So, the final answer corresponds to option D. Practice question 6. What is the determinant of matrix A? To solve this problem, we need to find the determinant of a 3x3 matrix. The process involves using a method called cofactor expansion, and in this case, we expand along the first row. We take each entry from the first row of the matrix and multiply it by the determinant of a smaller 2x2 matrix. Each smaller matrix is formed by deleting the row and column of the entry we're focusing on. These smaller determinants are then combined, alternating in sign, positive, negative, then positive again, as we move across the row. Next, we calculate the determinant of each of those smaller 2x2 matrices. For a 2x2 matrix, the determinant is found by multiplying the top left entry by the bottom right entry, then subtracting the product of the top right and bottom left entries. We perform this for each of the three smaller matrices, substitute their values back in, and carry out the multiplication. Finally, we combine everything by adding or subtracting those results, as indicated by the cofactor expansion signs. After simplifying, we find that the total determinant is 78. So, the correct answer is option A. Practice question 7. Given vectors A and B, find the value of the dot product of vector A with the cross product of vector A and B. We start out by computing the cross product of the two given vectors. The cross product results in a third vector that is perpendicular to the original two. We calculate it using the determinant of a 3x3 matrix, where the first row contains the unit vectors I, j, and k, and the second and third rows contain the components of the two original vectors. Once we compute that determinant, we find the resulting vector from the cross product has components -10, 7, and 9. The next step is to take the dot product of the original vector with this new cross product vector. The dot product is calculated by multiplying corresponding components of the two vectors and adding the results together. So we multiply the first components, which are 2 and -10, then the second components, which are -1 and 7, and finally the third components, which are 3 and 9. We add these three products together, and they end up canceling each other out to a final result of 0. Since the dot product came out to 0, it tells us that the original vector is orthogonal, or perpendicular, to the cross product of the two vectors. That makes sense geometrically, because a vector is always perpendicular to its own cross product with another. This answer corresponds to option A. Practice question 8. Find the third-degree Taylor polynomial, P3 of x, centered at x equals 0, for f of x, and then use it to approximate the natural log of 1.1. Which of the following is the best approximation? We begin by computing the derivatives of the function. The first derivative of the natural log of 1 plus x is 1 over 1 plus x. The second derivative is -1 divided by the square of 1 plus x. And the third derivative is 2 divided by the cube of 1 plus x. These expressions give us the building blocks for the Taylor polynomial. In the second step, we evaluate each of those derivatives at x equals 0. The function at 0 is the natural log of 1, which is 0. The first derivative at 0 is 1. The second derivative at 0 is -1. And the third derivative at 0 is 2. Next, we construct the Taylor polynomial using those values. Substituting in our values, we get x minus 1/2 x squared plus 1/3 x cubed. Finally, we use this polynomial to estimate the natural log of 1.1. Since 1.1 is the same as 1 plus 0.1, we plug in 0.1 for x. We get approximately 0.09533 as our final answer. So the best approximation from the choices given is 0.095, which corresponds to option A. Practice question 9. Given the following equation, z equals cosine of theta plus j sine of theta. Use Euler's identity to express z cubed in rectangular form. We recognize that the expression cosine of theta plus j times sine of theta is the same as Euler's formula, which is e raised to j times theta. So, we rewrite the original number in exponential form using that identity. We can then raise that exponential expression to the third power. That means we take e to the j theta and raise it to 3, which gives us e to the j times 3 theta. This uses the exponent rule that says when you raise an exponential to a power, you multiply the exponents. In the final step, we convert this result back to rectangular form using Euler's identity again. Euler's identity tells us that e to the j times an angle is equal to cosine of that angle plus j times sine of that angle. In our case, the angle is 3 theta. So, the final result is cosine of 3 theta plus j times sine of 3 theta. This result matches answer choice A. Practice question 10. Solve the following system of equations. What is the value of z? We start by isolating x in the first equation. This is a common technique to simplify a system, solving one equation for one variable and then substituting that into the others. So we take equation 1, solve it for x, and express x in terms of y and z. Next, we substitute that expression for x into the other two equations, equations 2 and 3. This eliminates x from those equations and leaves us with two equations in only y and z. When we substitute into the second equation, we simplify and end up with a new equation, negative 3y plus z equals 2. Then we substitute into the third equation. After simplifying, we get another new equation, 5y plus z equals 8. Now we have a new, simpler system, two equations with just two variables. In the third step, we solve this reduced system. First, we use the first new equation to solve for z in terms of y. Then we substitute that expression into the second new equation. This gives us a single equation in y, which we solve to get that y is equal to 3/4. We then substitute that value of y back into the expression for z. We multiply 3 by 3/4, then add 2. That gives us z equals 17/4. So, the final value of z is 17 divided by 4, which corresponds to answer choice B. That concludes our practice questions for this unit of mathematics. In the next lecture, we will continue with mathematics and cover topics within the scope of calculus. Again, if you want more example questions for mathematics or complete FE practice tests, visit the link in the description or on screen. Thanks for watching.